So once again, good afternoon, everyone. Am I audible to you? Can you hear me?
Yes, sir.
Okay, thank you. How are you? It is.
Fine, sir. How are you, sir?
Yeah, I'm fine too. So I believe you can see my 50 as well.
Yes, sir.
Uh, So Sempang Tapas censoring the Pandit and it is. Okay, I believe others will be joining. So shall we wait for 1 or 2 minutes for them to join, or we shall start?
Yes, sir. Wait, sir.
Okay. Okay. So in the meantime, do you have any confusion from the last classes? Any questions? So initially we have discussed about this chemical machining. Okay, there we know how we use a strong chemical reagent for our machining intended machining purpose. Okay, we know about its setup, process, etc. What are the different how we do it. Okay, we can discuss about all those each factor, etc. Okay, so how it is important in our case, all those things we have discussed. Okay, so I don't know how why the status bar is not hiding. Still it's coming. Okay, so later we have discussed about like the selection of criteria of selection of mass material, similarly the chain selection criteria, etc., and it's the process advantage, disadvantage, process capability, etc. So later on we have discussed about photochemical machining, in short PCM, which is another variation of your chemical machining only. So here what is the difference? Like some photographic techniques that we use here, and later on we have discussed how actually production of that particular or designing of that particular initial artwork for doing that for making that mask is important in case of PCM. Okay, photochemical machine. Okay, just wait. We have lost power supply in college. Okay, its internet is reconnecting now. Okay, you might not see the slide changing. Okay, let's wait here. Once it gets connected, I'll once again come start. Okay, after this pass, do you have any confusion in the chemical machining? Anyone?
No, sir.
Okay. So photochemical machining, what we are discussing actually, like here, there are certain other processes apart from the whatever the steps we have seen in chemical machining. Okay, it is somewhat similar, but certain differences are also there with respect to the production of the mask. Okay, and the way we do the whatever is the treatment of the particular developing of the particular which material. Okay, whatever is the coating we do, we cure it. Okay, we use that particular negative. Okay, which is kind of the mask. Okay, photo negative, and that is itself is the kind of photo tool itself in our case. Okay, and we allow that on the particular clean metal we use the photoresistive coating, and then we cure it and we expose it to your UV light. Okay, and in that particular case what basically happens, so as we have placed the negative before doing that particular UV irradiation. Okay, so what basically happens, so whatever from whatever portions actually the UV light passes through, okay, those portions actually the resist gets developed, and developed means actually that at those locations actually the resist gets stronger. Okay, you can say like that, and the other portions become kind of exposed now, and rest is somewhat similar to that of your chemical machining process. Now we are once again going to deep it inside the chemical part. So wherever actually resist got developed, and the portion which where resist actually the partially removed, from there the chemical will attack there and do the required machining. Okay, and after that resistors to be scrapped out, etc., which is somewhat similar. Okay, so I believe up to this point there is no problem. So today we are going to discuss about electrochemical machining process. So now, before discussing about electrochemical machining, so it's actually somewhat, actually the kind of machining, okay, and second definitely modern machining process only of removal of workpiece material, okay, and here what basically happens, generally atom by atom removal of the workpiece material happens through some electrochemical dissolution action. Okay, and this whatever is the electrochemical dissolution that is happening, that is with according to the principle of Faraday. Okay, the Faraday's laws of electrolysis that you have studied in your previous maybe class 11, 12 and all. Okay, so this process is a process is actually taking the advantage of, or you can say which is based on that particular Faraday's law of electrolysis. Okay, and we can say that it's a kind of controlled anodic dissolution which is happening in a complete electrolytic cell, and within that cell itself the workpiece will be made anode, and the tool, which will be kind of separate tool, will be made the cathode. Okay, that means here what we are going to do, as you have seen, as you might be knowing about electrolysis process. So do all of you, I believe all of you have heard about electrolysis process, the Faraday's law, etc. Yes.
Yes, sir.
Okay. So now I believe all of you have also heard about also electroplating process, etc. Okay. Now in that electroplating, etc., what basically happens? So we actually through the we take advantage of that particular electrolysis principle. Okay, and actually on a particular, the two electrodes will be there and that cathode. Suppose we what we can do, a thin layer of, or thin or thick, depending on what is how much, for how long you are doing that process. Okay, electroplating process. So generally mostly it's a kind of atom by atom this deposition happens. Generally is a thick layer of like plating layer of the whatever is that particular material. Okay, you can deposit on the other electrode, and that is how a plating you can do. Okay, electroplating. Now here, that kind of concept we are using for machining process. Okay, in electroplating our intention is we deposit material. Okay, in machining what is our intention? Our intention is, but it's just the opposite. We want to remove material. Okay, and it should be controlled way. We should be able to, that means the way we want to remove the material, it should happen like that. Okay, and that's why this particular ECM process, it's a kind of controlled anodic dissolution. Anodic dissolution means what? The workpiece from where we want to machine, we want to have the machining. Okay, that means machining means we want to remove the material from there. Okay, and in electrolysis what happens, it will be electrochemical dissolution that is happening. Okay, dissolution is just kind of removal of material only. Okay, and now here in that particular case, the workpiece from where we want material to be removed will be make anode, and the tool which is actually giving that, which will be having the separate shape. Okay, desired shape which one we want to give on that particular workpiece. Okay, so that will be made the cathode. Okay, and rest is actually the electrolysis, that particular consideration we have to take. Okay, so we'll just see how basically that is happening. And but the thing that you must know is it's a kind of anodic dissolution that is happening from the anode. That means where the metal is being removed, that means the workpiece material from where you want your material to be removed has to be made anode. If you make it cathode in that particular electrolytic cell, then your process will be reversed. There will not be any whatever you have intention you had. Okay, that will not happen. Okay, so this particular process, this electrochemical machining process, in short ECM, it's also known as a contactless electrochemical forming process. Why contactless? As we will see that there will be some inter-electrode gap that will be always maintained between the tool and the workpiece. Okay, that means both the in that particular electrolytic cell, we know that there are anode and cathode. So this anode and cathode, in our case, we will be making the workpiece anode, we will be making the tool a cathode. Okay, so that means they will be kind of metallic in nature. Okay, the tool, and they has to be kind of, they should be able to act like an electrode. Okay, so the material uh, like which what we can machine, okay, it has got certain limitation that is okay. Okay, so now here basically what happens, in case of electrolysis, we generally use electrical energy to produce a kind of chemical reaction. Okay, and here this particular in this particular process, it is based on that particular chemical reaction, forced chemical reaction, which we do, which happens in the electrolysis only, and that's why this particular type of machining process is known as electrochemical machining process. Okay, so now as I have already discussed, so you can consider it just like the all of you already know about electroplating process. In electroplating process, our intention is we want to have a layer of whatever is the depositing material, okay, over a particular metal. Okay, we have to plate it. Okay, plate it with a, suppose just like the plating of like as you have heard, no, suppose silver plating, maybe a gold plated jewelry around. So there what happens on the surface of the other one, okay, just a tiny layer of, okay, by atomic layer thickness. Okay, so that kind of very tiny layer of suppose other material. Okay, suppose if it is gold plating that we're talking about, then gold will be deposited, okay, to the help of that electrolysis process. So now that is the electroplating, where we want the metal to be deposited over the other one. Okay, now here it can be considered in ECM process. This ECM can be considered as the reverse of this electroplating process. Okay, so now that means we have to take care of that anode and cathode. Okay, the workpiece has to be made the anode, the tool will be cathode. Okay, and where the dissolution will happen, dissolution of metal, so it will be anodic dissolution. That means at the anode, from whatever is being made anode, actually from there removal of material will be expected. Okay, so now even though you are saying that it's just we can consider it as a reverse of the electroplating process, but there are certain like certain, you can say, differences between the ECM process, that is electrochemical mixing process, and other type of electrolytic process like the electropolysis, electrolytic weakling, etc. So what are these particular two differences, basic differences? Okay, now here our intention in case of ECM is not just to remove the metal from the workpiece. Okay, but our intention is something else. We are not only just randomly removing the material from the workpiece, okay, but also we are changing the shape and size of the workpiece in a very controlled manner, in a very precise manner. That is one of the very important aspect of it. Okay, it cannot be like random kind of removal. We don't want. Okay, whatever is the shape that we want to keep on that particular workpiece. Okay, based on that we go for do by this particular ECM process, by this particular removal process, we all even alter the shape and size of the workpiece also, and it has to be, everything has to be done in a very controlled manner. Again, secondly, the magnitude of the minimum current density, which is generally employed in CM, is very high compared to the other processes. Okay, so other processes, other which we are discussing with respect to other electrolytes. So these are two basic major advantages with respect to EDM process and the electroplating process, etc. Even though we can consider as if EDM is reverse of that of the electrolytic process. Okay, up to this much, I believe all of you can understand, right? All of you have
Yes,
understood
sir.
the gist of it. Okay, what about others? Okay,
Understood, sir.
okay, thank you. So now here I am showing in this particular, through this particular figure. So actually we are showing the principle of electrolysis. So all of you already know whenever we are talking about electrolysis, etc. Okay, so that there will be a whole electrolytic cell will be there. So this cell actually comprises of the whole electrical system, their wiring, etc. And both the the with the electrode, that is one is the anode, another is the, this one is the cathode. Anode means what? This is connected to which terminal, positive or negative? Anode, it is positive. Which one? It is connected to the positive terminal. Okay. Okay, and cathode connected to the negative terminal. That means the anions come to the anode, cations comes to the cathode, that you already know. Anion means they are positively charged or negatively charged. Anion is positive or negative?
Negative, sir.
Okay, and cation is fluid. Okay, so this cation comes to the cathode, anion comes to the anode. So those things you already know from your previous study. So in this cell, so apart from having these two electrodes, the connection of it, okay, through whatever is the power source, okay, AC or DC. Generally, in our case, in ECM, we go for DC, okay, and there will be a electrolyte. So electrolyte is nothing but this particular kind of liquid kind of thing that you're seeing, okay, and it will be immersed there. So this completes this particular cell, okay, and what happens? So if suppose this is the anode, okay, so in our case, we'll be making the workpiece as the anode, and this will be whatever is the tool will be given that whatever is the required final shape that will be required, okay, so that kind of thing we are going to give in this method. Okay, just a second. Can you hear me now?
Yes, sir.
Okay, thank you. Okay, so as we're discussing, okay, so here workpiece will be making the anode, okay, and the tool has to be made as cathode, okay, and resolution of the workpiece will happen from the anode. That's why this ECM process is also known as anodic dissolution process. Okay, so now if we discuss about the principle of ECM, okay, so if we consider here, okay, so what happens at anode? Okay, so this chemical reaction, I believe all of you can just the redox reaction that is taking place there. Okay, so I believe all of you can just go through it. Okay, so what will happen? Fe becomes Fe twice plus, and it will just two electrons will be released there. Okay, plus two electrons. At cathode, what will happen? Two H2O plus it is going to take that particular electrons. Okay, and hydrogen gas will be produced along with these hydroxyl ions. Okay, and if you combine both the reactions, what do you get? Fe2 plus plus 2OH minus, okay, gives rise to this FeOH2. Okay, and if we consider the whole, that's the net reaction of the above three, then Fe plus 2H2O, okay, it gives rise to FeOH2 plus hydrogen gas. Okay, then the ferrous hydroxide reacts with water and oxygen, and what will form? It is going to form the ferric hydroxide. Okay, so this is the final reaction that is taking place. Okay, so these are just your conventional whatever is the electrolysis that you have already seen. So this electrolyte may be sometimes NaCl that way. sodium chloride, etc., whatever. So depending on what is the electrolyte that you're taking place, okay, that way in the in the case of ECM, okay, so that way this electrolysis will happen. Okay, so now here in the below figure, you can see actually we are showing the complementary shapes which are being produced in ECM process. Okay, complementary shape means what? So see this has part the above portion. These are the tool electrode. Okay, so tool and workpiece both are nothing but both are acting like electrode only. Sorry for the inconvenience. I believe now I am once again audible. Hello.
Yes, sir.
Okay, thank you, thank you. So as you can see, so here the tool and the workpiece both are nothing but two electrodes in our case. Okay, so tool is negatively charged, that is it is the tool will be negatively charged, that means it is the cathode or anode, it is cathode. Okay, the workpiece we are making it anode. Okay, and now the dissolution of the workpiece material will happen from this particular anode. Okay, from here. And so now here what we are saying, actually this is the initial condition, and right hand side whatever is being shown, okay, this is the final condition of the tool and the workpiece material. So this is we are showing that the complementary shape that is being produced by ECM on the workpiece. Okay, so actually what happens finally, whatever is the type of shape you require, okay, so the complementary shape you are going to keep in this particular tool. So if this tool shape is something like this, finally as you can see in that workpiece also the resolution is happening like this. And whenever you are feeding that particular tool, okay, tool electrode, we are expecting this kind of result. Okay, that means this ECM can very easily give you any kind of intrinsic replica kind of shape on that particular workpiece. Okay, so but the thing is you must remember workpiece is another cathode. Workpiece has to be made another cathode. Workpiece is what? Another cathode. It is anodic dissolution that is yes, correct. So workpiece is anode. Okay, so now here in this slide you can see the schematic diagram for a complete ECM system. Okay, so here the main elements of ECM system is power supply has to be there. Okay, because if we have to think of this particular the electrolytic cell, so one of the very vital element is the power supply. Okay, so generally we go for DC current. Okay, so for electrolysis we generally don't prefer AC because if we go for DC, so the redox reaction that is required that is going to take place. Okay, so if we go for AC, then it will be like the conduction only that is going to take place, which is not required. Okay, similarly the electrolytic supply system will be there. So for that we will be having the reservoir, all the filter pump system. Okay, and from there it will be electrolyte will be pumped there. So similarly the cathode, okay, the tool and the tool feed system. Okay, so the tool feeder, etc., everything has to be there. Because the why the tool feeder is required, because see as the workpiece is being getting be digitalized. Okay, so that means the gap between the tool and the workpiece has to be this known as inter electrode gap. So because both the tool and the workpiece, they are nothing but the two electrodes for this particular whole system, right? So tool being the your cathode, okay, workpiece being the anode. Now, if suppose let's consider the workpiece in the anodic dissolution that is happening, that means the metal is being removed from the workpiece. So in that particular case, we have to maintain a certain gap between the tool and the workpiece. Okay, certain minimum gap will also be there, and if the distance is too large, then once again the proper kind of resolution will not happen. Okay, and that's why generally feeding the tool towards the workpiece also is kind of important. Okay, similarly, anode that will be there. Okay, anode is nothing but the workpiece which is electrically conductive. Okay, and we have to have the whole work handling devices, and generally the work holding devices is non-conductive. Okay, but the anode, the workpiece material has to be conductive. Okay, so now here you can see one of the ways of feeding the electrolyte, which can be fed through that particular tool, which is a this is a kind of insulated kind of tool. There may be kind of bare tool, there may be insulated tool. Right now here in this particular case, you can see this is the insulation that we are providing so that the side arcing doesn't take place. Okay, so here you can see when we are passing the electrolytic or pumping the electrolyte through here. Okay, this may be one way of passing. Okay, then after that, whatever is the electrolytic dissolution that is taking place. Okay, so from here the electrolyte will be splashed away. Okay, along with that the debris etc will be splashed away. Okay, and we'll be giving constant feed motion to that particular tool, and tool is negative, workpiece is positive. That means workpiece is anode, tool is cathode. Okay, so here you can see different types of tool design. So in ECM we can use bare tools, we can use the coated tool, also we can use the bead type tool. Okay, so here in this particular figure you can see machining, what is happening when we are doing machining with a bare tool. Okay, so in bare tool what happens, even though your suppose machining is taking place from here, okay, from the side walls becomes parabolic profile. Okay, our intention was to get this kind of shape. Okay, so sharp. Okay, but now this walls becomes parabolic because of the side arc. Okay, from here also metal keeps on hitting this wall. Now that kind of problem can be somewhat overcome by side insulation, by placing side insulations, okay, on that particular thing. Okay, that is kind of the coated tools. Okay, so in this way if we use the coated tools we can go for high aspect ratio straight kind of hole. Okay, so as you can see, once again if you go for hollow kind of tool, this is solid tool, this is kind of hollow tool. If you don't produce any insulation, what happens you can see, so here the shapes are kind of, the walls become somewhat parabolic. Okay, but these problems can be overcome if you give side insulations to it. Okay, so here it is the insulation, this is the insulation, here also this is insulation, this is insulation, so this is the only exposed part, so this way machining is taking place. Okay, sidewise there is no machining in case of coated. Okay, so similar is the case, or you can even go for some contoured kind of machining also. Okay, so these left hand side all are actually we are showing tools which are without insulation, right hand side tools with insulation. Okay, so with insulation controlling is good. Okay, so and similarly here we are showing the bead type tool. Okay, so this is the bead type tool, so high aspect ratio kind of drilling, high aspect ratio hole is possibilities. Okay, after this most all of you have understood.
Yes, sir.
Okay, thank you. So now in this ECM process, there are generally sometimes some error which are seen. Okay, which is seen in this error means error in the whatever is the profile that we wanted to get, and suppose we are not getting that. Okay, that kind of error. So now that errors in this particular machine may be due to heating of the electrolyte. Okay, so as the electrolyte process is going on, okay, the redox reaction is going on. Okay, the electrolyte may get heated up, and because of excess heat generation, it hampers the effectiveness of that particular process. Okay, similarly as you can see in that process actually, if you can recall the previous cases, okay, hydrogen gas was released. Similarly if it is NaCl, that was the salt, sometimes chlorine gas etc will be released. Okay, so in those cases, so variation of gas bubble concentration, because of that also we can have some error in machine. So that is shown here in this particular figure. Okay, so excessive gas bubble may form here, which may hamper the proper machining of this particular. Okay, so whenever this is the excessive machining gas bubbles that is there, okay, in this process it is acting as if something like insulation. Okay, so here machining will not take place, and below it, okay, which is actually kind of free from the gas bubbles, here machining will take place. So this kind of we expected this kind of dotted line, that is the straight kind of profile, but we are getting something else. Okay, similarly, there may be some variation in the sludge concentration, and just like this. Okay, and because of this, sludge is from the workpiece side. Okay, gas bubble in the tool side. Okay, so because of that also similar kind of phenomenon may happen. Okay, so this portion will not get eroded. Okay, so the tool gets damaged. Okay, so now all those cases, okay, this error sometimes can be compensated for by doing the proper modification on the tool session. If you know, suppose sludging is going to be happening here, okay, so maybe modified tool surface you can do like this. Okay, similarly feed variation at different surfaces, because of that also sometimes error is observed. I don't know whether this is some of the, this might not be that much visible properly, but let me tell you. Okay, so tool design, there are basically two issues. One is definitely the tool shape, okay, and one is the tool material. So what are the issues with the tool material, or what is the condition that we want here? Okay, so the tool material has to be good electrical, as well as it should have good thermal conductivity. Okay, otherwise if it is not electrical conductivity, how can it behave like a kind of electrode? Similarly, it should have a good stiffness, because see, we doing constant flushing, etc. Okay, so flushing, that electrolyte will be kind of pumped, okay, at a comparatively higher pressure. So if it is not stiff enough, then what may happen, it may get distorted, and if the tool itself is getting distorted, okay, then the shape will be whatever shape you wanted to have on the workpiece will not be good done proper. Similarly, for fabrication purpose, the tool material should be easily machinable, because whatever is the shape we require, based on that the tool also has to be produced. The tool should be given certain shape. Okay, from there only complementary shape we get on the workpiece. So the tool material should be easily machinable. Similarly, it should be highly corrosion resistant, because all those NaCl or other salt solution will be there as the electrolyte. If it is not corrosion resistive, okay, then the tool material itself will get corroded away. Okay, and some passive layer over it, there should not be any formation of passive layer on it. Okay, and generally copper, aluminum, brass, platinum, etc. These are some of the tool materials. Similarly, there are certain uh, we also know that the electrolyte is being used there. Okay, so this electrolyte also performs certain function. Okay, it's not like only it's just there. Okay, we are dipping the cathode anode in the electrolyte, that's why the electrolyte is there. It's not like that. Okay, so what are the function of the electrolyte? So definitely what the vital thing is, so definitely it is completing the whole circuit, electrical circuit. Otherwise, if there is no electrolyte, so actually the passage of that particular electron. Okay, so it is not going to happen. Okay, the electrolyte, the circuit will be kind of not complete, so electrolyte this completes the circuit. Okay, apart from that, so it allows the desirable machining reaction to take place. Okay, also whenever it is like there is a heat generation that is happening, okay, so these are generally solutions that we use. Okay, it also acts as somewhat coolant. Okay, it carries away the generated heat. Okay, also the byproduct of the particular reaction also it carries out. Okay, and some of the desirable properties, like it has to have high electrical conductivity, the viscosity should not be high, it should have low viscosity, specific heat should be high. Okay, similarly it should be chemically stable. Okay, so there should not be any passivity in film formation on the work and tool surfaces because of the electrolyte material. So these are some of the, similarly environmental friendly. Cost also is another factor. So these are some of the desired properties of it. Okay, up to this, Masala, you have understood.
Yes, sir.
Others? What others? Hope you have understood. Okay, in the meantime, let me take your attendance. Okay, so I'll be calling your name. You just respond to it. Sami, absent. It is sir,
Yes, sir.
present. Biswajit present. Catherine absent. Tapas
Yes, sir.
present. Subham,
Present, sir.
Andreas, Ashish, Ashish absent. Handip,
Yes, sir.
Vishal absent. Semfang, Semfang.
Present, sir.
Okay. Jodian.
Present, sir.
Okay. Semfang is present. Jodian absent. Sensing Dao,
Absent, sir.
Present, sir.
Mario absent. And Zoidip.
Yes, sir.
Okay. So yes. So some of the advantages and limitations that also we can discuss. So whatever is the very advantages, it can very easily like machine highly complicated and curved shapes in a single pass. Okay, that is one of the major advantages. And generally, tool life in case of our tool life in case of EDM is very high. A single 10 itself 10 tool we can use for a large number of uses. Okay, and workpiece machinability, it's independent of its physical and mechanical properties because we are talking about this doing kind of electrolysis here. Okay, chemical process, anodic dissolution only. Okay, so even though it's kind of very hard and all, okay, it doesn't do that much problem. Okay, and generally whatever is the machine surface, they are stress and burr free and very good surface finish we generally get. Okay, some anodic dissolution that is happening, okay, atom wise, so very good resolution we get. And generally scrap is nil. Okay, so it reduces the inventory expense. And it's kind of automatic only. Later on you see that even it's kind of automatic operation that is happening. Okay, so and the overall machining time if we discuss, generally is slow. So some of the limitation that includes like as we are talking about making the workpiece one the anode and cathode, etc. So workpiece anode tool cathode, so it can only machine electrically conductive work materials. Okay, so if it itself is not electrically conductive, then it cannot work like an electrode, right? So as that is the there one workpiece has to be like anode, or tool has to be cathode, so it has to be electrically conductive. Okay, and the whatever is the component accuracy, machine component accuracy that you get, okay, it also depends upon the tool design and how much controlling you have done on the process, and what is the complexity of that particular product that we are talking about. Okay, so these are some of the limitations, because if that is not done properly, then machine component accuracy will be lost. Okay, and sometimes what happens, so if there is the whatever is the work material, it has got hard spot, some inclusion, under scaling particle. Okay, so in the spaces, okay, it process becomes somewhat disoriented. Okay, and like that, and sharp corners etc. cannot be produced. And as we are talking of using like light and some case etc. generally is evolved, so generally it's not that much environment friendly. Generally, it's used for like machining hard and tough materials with complex contours. So we can even go for like different varieties of ECM, like ECM turning, repairing, posing, grinding, etc. Okay, so different varieties of work can be performed by a modified version of ECM. Okay, and generally in the aeronautics industries, nuclear industries, automobile industries, and turbine industries, generally this ECM process is very greatly employed. So some of the typical application includes turbine blade, high strength temperature resistant alloys. Okay, machining of turbine blades which are made of high strength temperature resistant alloys. And external and internal surface scoping you can do, because we have seen that complementary surfaces it can produce. Okay, so curvilinear slot we can cut, machining of intricate patterns, etc. Okay, so these are some of the, and what depends on the EDM parts, what happens to the mechanical properties of the EDM parts. So there is no hydrogen embrittlement. Okay, so because the hydrogen is getting evolved at the cathode, not at the anode. So anode is our workpiece. So hydrogen embrittlement of workpiece is not there. Okay, so like ductility, strain, etc. Then they are not affected. Okay, even the surface layer which are generally damaged in normal conventional machine process can be even removed by ACM. Okay, so does it improves the properties of the work material, also reduces the fatigue strength of conventional machine component having compressive resistance. Okay, and generally the EDM machine surface, it is seen that generally better wear and friction as well as corrosion resistant properties are important. Okay, so with this we'll stop here for today. We have completed the process. So in the next class maybe another version of PCM, that is electrochemical grinding, that we are going to discuss. Okay, so if you have any question you can ask. Otherwise we'll stop here. Have you understood?
Yes, sir.
Okay, then thank you everyone for joining. So and happy viewing.
Thank you, sir.
We'll stop here. Okay.